Good morning, everyone. Thanks, Mr. Chair, for the introduction. So the idea of this presentation today is to discuss a little bit on the preliminary results I have from my sabbatical last year. Last year I was having some fun in Switzerland at EMPA, the laboratory from the government in Switzerland. And I did a collaboration to try to use a coupled CT scan and SEM to understand ASR-induced damage with Andreas Lehmann and Michele Griffa. So I think this is a very short introduction. Everybody here knows that ASR is a very important problem. In Canada, for instance, we have ASR in every single structure we look around, including our own campus. So we need to find a solution for that, but more than that, we have so many structures already with this issue, so we need to understand how to cope with ASR in critical infrastructure. So this is just a couple of photos from, this is a very iconic, I would say, bridge in Canada that has been, by the way, demolished because of ASR-induced deterioration. So in the micro scale, ASR develops this way, random cracks, very important cracks that sometimes will get some structural implications. But to try to understand a little bit more how this process goes on, lots of research have been developed in the mesoscale, trying to understand, okay, if you have alkali-silica reaction from the coarse aggregate, where the crack, where is actually the crack generated, how it propagates, and how that implicates engineering properties such as compressive tensile and modulus of elasticity. We have done that a lot over the past decade or so, and we have now a much better understanding on how ASR actually starts and develops really an engineering problem. However, working the mesoscale is still not enough. So I think we have now much more tools for a better decision making, but for a further understanding of the mechanism of induced deterioration, we need to get to the micro scale. And whenever we go to the micro scale, there's lots of research out there as well, you know, looking at SEM to understand the different types of reaction products formed. So we know it's published that whenever you have your silica gel that is close to the cement paste, you have a little bit more calcic material. Whenever you have, whereas whenever you have gel within the aggregate particle towards the middle, you may have down the road more crystalline materials. There are some folks that already studied the atomic ratios in percentage to classify crystalline versus amorphous materials and so on. So this has been published and this has been known, but we still have some issues. First, whenever we go to the microscope to understand, especially SEM to understand the composition of the materials, is still very qualitative in the sense that how do we link that with induced deterioration? Because at the very end, for an engineering perspective, we need not just to understand the products being formed, but how that will imply in engineering problems in the future. So it's very difficult to quantify damage in that scale. So because of that, and plus, whenever we do that, it's the same specimen is kind of destroyed. We can do evaluations over time on the same specimen. And the CT may provide us that perspective. So in the past, colleagues from EMPA, they try to run some CT. So basically what you do, you get your samples, you induce, you put in an environment generating ASR, and then from times to times, you scan that sample, and then you may do some computations to try to quantify not only the amount of gel formation and location of gel formation over time, but actually cracks development. So this has been done, but what was the problem? The problem is that this was mainly done for coarse aggregates, so nobody had a little bit the information whether a technology like this could be used for sands, reactives, highly reactive sands, for example, Texas sand. And people start, you know, keep asking questions whether we could use recycled aggregates that may have potential for alkali-silica reaction, and that would be interesting to use CT scan to understand the development of the deterioration of recycled aggregates too. Plus, what we try to do in this research is that previous research using CT, the problem was to distinguish really the secondary products. So in the aggregate particles and the cement paste. So what we try to do is using cesium nitrate and barite as tracers as well. So they would generate much whitish products, and that will facilitate the evaluations. So with that being said, what's the objective? The objective was to perform some samples in the lab, and then from conventional concrete and recycled concrete, both with sand and coarse aggregates, reactive. In terms of recycled concrete aggregate, it's just important to mention that whenever we look at particle, as you can see here, by the way, this is works from Cassandra, my student that is there. So we see that we have an original virgin aggregate, but we also have lots of residual mortar. And if you have an aggregate that is reactive, the question is, can we use that if we crush? Can this material maybe be crushed and reuse it? But maybe the reactivity for a potential secondary deterioration will come from the original virgin aggregate. But if what is causing the issue in the primary concrete is a sand, which is embedded in the mortar, in the residual mortar bar, well, not mortar bar, sorry, the residual mortar, we don't know if that will implicate a secondary expansion or not. So what we tried to do, it was really that, focusing on further reactivity on the original virgin aggregate or in the mortar. So what we've done. So we designed 35 megapascal concrete with different reactive aggregates, so pretty much 4 families: conventional concrete with a fine and a coarse material, and a recycled concrete with reactivity in the original virgin aggregate and in the residual mortar. Then we placed, we soaked that at 0.4 molar. And why 0.4 molar? Because research has been done previously in which we try to mimic the molarity in the pore solution, so that we will, I would not say stop, but at least minimize diffusion, right? And then in the evaluations times of 3-4 weeks, 11, 12 weeks, 16 and 24 weeks, we've conducted CT and SEM, and we are going to be interpreting the results. Good. So talking about results, and starting with conventional concrete, let's put that way, it's interesting to know that the expansion over time can be huge, right? First of all, as expected, the Texas sand is almost a bomb, and we would have deterioration over time. Springhill is a coarse aggregate, very reactive as well. This is, by the way, a Canadian aggregate, the one that has been used to build Mataquac Dam. And we can see that there is very important deterioration over time and expansion over time as well. But interestingly, if you look at the recycled concrete bearing a reactive aggregate as an original virgin aggregate, we have lots of room even to take over that expansion over time. So if the question, just in a qualitative fashion, was, can we keep having issues over time? The answer is yes. If you crush it and reuse it, there is still an issue going on. Plus, if you have your reactivity in the residual mortar, you can still have lots of further deterioration as well. So meaning that if you had any reactive material in a recycled material, this should be treated carefully, because you can have indeed secondary expansion. So basically what we have done then is to select a couple of points for analysis. So my idea today is just to give a hint. I have just preliminary analysis here, and hopefully by ICAR or later in the future, I would be able to complete, especially my quantitative analysis. So, I mean, for, let's say, the conventional concrete bearing Texas sand, we were able to see, as expected, lots of cracks within the aggregates with secondary products. We calculated the alkali-to-silica ratio and calcium-to-silica ratio, and they fit pretty much in the ranges expected. Interestingly, and we were trying to see that whether those chemical components will change as a function of time, and so far we didn't see a trend. So they probably the period that we studied things was not, long enough to catch those differences as a function of time. So we were pretty much along the same range, and indeed they were alkali-silica reaction products. Another thing of interest is that you can see very whitish products. Those whitish products that are very easy to recognize because of the cesium nitrate, right? Normally we may detect those, and April know that a lot, by morphology, by experience and so on, but the use of cesium nitrate really helps in that detection of the gel within the particles. And interestingly, for example, this is a particle of 3 weeks only of ASR with Texas sand, and you see that in the particle we have some cracks, and if you do a cesium scan under the SEM, you're going to see that cesium is really penetrating. So we are having an alkali balance between cesium and sodium and potassium, and cesium is really being fast in penetrating. So it looks like a good tracer for future analysis. For the recycled concrete aggregate bearing Springhill, pretty much same trend. We were able to compute the alkalis to silica ratio and calcium to silica ratio, and again they belong to same composition. What you're trying to do of conventional concrete, what you're trying to do next is to check whether composition of gel within the aggregates in a recycled medium would be different from composition of the gel in the old cement paste and the new cement paste of a recycled medium as well. So let's see if you're going to be able to do that in the future, but more or less we couldn't see so far at least a trend that would differentiate the chemical composition of the materials as a function of time. Now, for the CT scan analysis, what you have done is that we needed to select, the quality of the images, so that we would be more or less precise to get our deterioration level. So the voxel sizes is 22 microns, so we are able kind of to detect damage that bears that number or above. The spatial resolution is 50 microns, so we did lots of radiographs, and then it's a very neat and yet complicated process. Whenever you get your images, there is lots of computations to be done. So first of all, you need to declare a region of interest, and then you need to just reduce noise, do some rendering, image registration, so on, to guarantee that all of the images, they have the same origin, right? And then finally, you do your computation. So far, I was able to do all of these dark parts, and now in the future, I will come up with a more quantitative in which I'm aiming to get not only the amount of products, but the amount of cracks as a function of time. So the increase in percentage of cracks as a function of time. And then we can compute cracking density and things like that. So just a couple of images, preliminary and qualitative images for you. For example, if you focused on this particle, for instance, with Texas sand, conventional, you see that this particular particle doesn't bear any cracks at 4 weeks, but whenever we come to 11 weeks, 16 weeks, and then 24 weeks, we can actually, it's very interesting because it's not a picture anymore, it's a movie, right? We can tell the story from the beginning to the end of ASR, and we could also catch what we call secondary deterioration. So whenever we see in structures, sometimes we see more deterioration at the surface when compared to the core, is because it may be due to different things, but there is secondary effects due to geometry, due to confinement, due to so many things. And we could see as well, if you focus, for example, on this part of the sample, 4 weeks versus 24 weeks, we start having cracks that are generated from the surface. So this is pretty much a shrinkage and reduction of the sample itself, which is a secondary, I would say, mechanism resulting from ASR. It's very interesting, hopefully this is going to work. It's very interesting to see that if you focus here on this pore, you see how this evolves over time. So It's pretty much this. I took 3 photos from this little movie here, and you can see that it tells you a story on how ASR is being developed in a 3D fashion, and that could help us a lot, maybe to scale that up to a more engineering, let's say, procedure. Okay, now regarding recycled concrete aggregate, it's super interesting as well. For example, if you focus on this particle here, you will see that we have the original virgin aggregate, and then we have the residual mortar. Pretty much the first thing you can see whenever we talk about recycle is that it's much more already a porous microstructure, right? But you see that indeed, as time goes by, you can see the formation of cracks, particularly in the the original virgin aggregate. So we were also able to find some cracks in the residual mortar, but most of them so far at least were actually regenerated in the original virgin aggregate. So very interesting. Another thing of interest is to see that the old mortar, we keep being producing as well products in the old mortar. And we don't know if the new alkalis in the system, they are kind of reaching the old mortar, or the old mortar bears alkalis enough to keep generating, but the reality is that we have, it's just a comparison here, we have, gel formation, pore filling in the old mortar too. So, with that being said, one of the things as a preliminary results that we got is that to check that barite and cesium nitrate are very nice tracers. We can compute much better things. By the way, there are 3 papers published out there from EMPA and previous works, and one myself with Andreas, trying to first of all understand the use or not use of tracers in the computation of CT. So you need to use that if you want to be really quantitative. And second, what are the hypotheses for a secondary deterioration of recycled concrete aggregate? So all of those hypotheses used in this work, we described a little bit in the previous publication. So it's very interesting. Now, most of the qualitative work in my CT slices are done. Now my job is to compute that. So I will be able to quantify volumetric amount of gel over time, locations of gel over time, cracks in different locations, and crack density. And hopefully I will be able to correlate that with mechanical properties as well. And since this work is in the micro scale, and I previously mentioned that lots of works were already done in the meso scale and macro scale, I think a very interesting correlation could be achieved. And for the SEM, what we're trying to do is to understand a likely difference of composition of gel as a function of time, and especially in the reactive aggregate, is to understand whether the gel would be very different if it's in the virgin aggregate or in the mortar. Hopefully, I can complete all of this evaluation by iCard. This is at least what I promised in the papers. And by the way, I just would like to take advantage to let you know that iCard will be in Ottawa next year in May 18 to 24. We are more than welcome to be all of you guys there. And if you have any questions, I will be glad to take those. Thank you very much.